My name is Steve Thompson. I'm a solution consultant for VIAVI Solutions, and I provide application support and testing support for the JD785 series base station tester. And so today we're going to go through some additional front panel navigation, sort of a review of the first session on navigating and selecting measurements, and talk about the specifics on the keys and buttons on the front panel. And then we're also going to talk about power measurements. So that is the agenda, is front panel navigation and understanding power measurements and how to make them. So again, today I'm going to go through the hard keys here at the bottom of the screen and give definitions on those, and we'll take you through a little bit of a tour of that. And also the hotkeys here on the right-hand side. And these are dual-use keys. There's 11 of them. Basically, they're also the numeric keypad, but they're a dual-function key. So we'll take you through the definition of each of those. So the primary key on the front panel of the hard keys is the mode key. This is very similar to the home button on your mobile phone or any other device you use. Takes you back to the very beginning of entry into the device, and allows you to select any of the standard or operational modes of the test set. So once you select the mode key, it's going to basically display all the test set measurement modes, everything from spectrum analyzer, interference analyzer, there's signal analyzer capability for all the various technologies, cable and antenna analyzer, your RF over fiber, be it CPRI or OBSI, channel scanner capabilities. There's also power meter and fiber inspection. And so there's all those various modes the test set can operate in. We also have the frequency or distance key. And this is basically where you can enter in the frequency or channel number for the signal you want to analyze. So it allows you to set the span. Once you're into that measurement or frequency mode, you can go ahead and change the span, set the center frequency, those types of parameters. We also have an amplitude or scale button, and this allows you to set the amplitude of the measurements. We also have the capability on this particular button to turn on a preamp, and so this allows you to increase the input signal at the first stage into the test set. That improves your signal to noise ratio, so it increases the signal as compared to any noise the test set may generate internally. And it does have auto attenuation also into this setting. So if you have too much signal coming in, it'll automatically attenuate it or turn off the preamp. Again, you can set an attenuation value also on this. You can also use the bandwidth or averaging key. And so this allows you to improve the noise floor measurements. So with any spectrum analyzer or channel power measurement, there is the capability to reduce the resolution bandwidth. And the smaller the resolution bandwidth, the finer you separate the various blocks across the screen as you're measuring power, the more accurate your spectrum analyzer power measurements will be. So again, you can go all the way from 1 megahertz resolution bandwidth down to a 1 kilohertz pretty easily under the bandwidth settings. You can also turn on video bandwidth, and you can set your averaging on this. So you can go from, say, the normal is an average of 1, so you're getting a real-time update, up to a pretty big number as far as a running average on this, and it smooths out the trace you're evaluating. We also have markers that you can go in and set on the screen, and this just allows you to pick out specific frequency points along the screen with a marker. And these are available both in the spectrum analyzer mode. If you have a bar chart, you can use the marker control to move across the bars. So measurements such as an LTE data measurement, where it looks at each of the resource blocks firing off. You can look at the specific parameters in each of the resource blocks by using the markers to move across the screen. We also have trace and display capability. So what this does is it allows you to have multiple traces of the same signal across the screen. You can have a peak hold, a min hold. You can have these to where they automatic reset after so many seconds. So there's a variety of ways to display the data across the screen. We also have a peak search capability. And again, this is standard with most spectrum analyzer type interfaces, where you can search for the peak, you can move to the next peak to the right, next peak to the left, those types of measurements. And we'll show you all these here in just a minute. As far as the hotkeys go, the primary two we talked about in the first sessions was the measure and the measure setup hotkeys. This is the number 1 key and the number 4 key. The measure key, once you're in a mode, there's multiple measurement types under that mode. So for spectrum analyzer measurements, you not only have the spectrum analyzer display, but you can also make a channel power, occupied bandwidth. There's a group of measurements that are considered spectrum analyzer type measurements. Same way for the signal analyzer. If you go into the signal analyzer and select the LTE technology, there's a large group of measurements that you can run under the LTE signal analyzer. There's everything from modulation analysis, power versus time. There's some auto measure capability. There's over-the-air measurements, carrier aggregation, RAN performance. There's a whole group that you can run. And so to select those, you start out at mode, then pick the measurement type, whether it's spectrum, interference analyzer, or signal analyzer, etc. And then once you're into the specific type of, say, signal measurement, an LTE FDD, for instance, you can select the number 1 key, the measure key, and it'll show you all the measurement capabilities for that technology. And for each of those measurement types, there are specific parameters you can set. So after you've selected the measurement type, then you can select the number 4 key, which is a measurement setup key, and you can change specific parameters that are unique for that particular measurement. So the number 7 key is the save load key. This is very handy for being able to not only create specific setups and save them specific for your market, but you can also save screen captures. You can log the data for the particular measurement that's on the screen. You can save it as both a CSV or a device-specific format that we have software that you can use to evaluate the measurement then. So it also allows you to take measurements that someone else has set up on a different test set and load them into this particular test set you're working with. So you can have the measurements created one time, transfer them into your test set, and then go ahead and load those up, and they can be specific for your market. So if you have 3 test sets, you don't have to recreate every test on every test set. So sweep key, that is the very bottom left key. It's where the decimal point is. And again, this just allows you to change the sweep mode from continuous to single measurement mode. And so you can do a single screen capture of, say, a spectrum display or do a single measurement. We also have on the number 2 button a trigger measurement. And you can trigger internally, externally. You can trigger based on GPS. There's various ways to trigger the measurements on the test set. The number 3 key is your system key. And so this takes you into your system configuration. You can change your screen type from outdoor to indoor to nighttime. You can look at all the hardware info, the software info, all the licensing, all that's found under the number 3 system key. You also have a preset key, so if the test set ever becomes locked up and in an indeterminate state, you can select the number 6 preset key, and basically it's like doing a factory reset on the test set. Takes it back to no saved registers, empties out the memory, and puts it back into the same state you would have got it right out of the box. You can also select the number 9 hold key and go from continuous measurements to single measurements. So it basically freezes the screen once you hit the hold key, and hitting it a second time lets the measurements run real time again. And so if you want to stop a measurement and look at something more closely, you can hit the hold key and be able to do that. We also have a number, well, it's a plus minus key, but it's also the limit key. So you can put limit lines across the screen that allow you to set this device up, say a noise floor measurement, and if at some particular point in time you're getting a loud spike or spur that comes into it, you can set a limit line on your display, and if that limit line is broken, you can have the test set automatically log data onto the USB stick. So say in the middle of the night you're getting an alarm where the noise floor is rising substantially, you can set it to where this limit line's above, and if the noise floor rises, it'll trigger that measurement. You can also build a multi-segment limit line that will form around pretty much any shape you can think of going across the screen. The number 8 key allows you to turn on the keypad lighting, so you get the backlighting for the keypad if you're working at night. And again, the 0 key is your help menu. You can select that and read help off the screen if you need to. Again, I do recommend going to the updatemyunit.net and downloading the user's guide and putting it on your laptop. I find it a lot easier to read it off the laptop real time and be able to make the button presses on the test set at the same time without having to go back and forth. So the last but not least, again, is the front panel measurement fields. So as you can see here in the top left, you can actually see what mode the test set is in, whether it's spectrum analyzer, interference analyzer, cable and antenna analyzer. Then you can look at the specific measurement your test set is in. And then on the far right, you can see the last key press that was entered in. So on this, the user went to the spectrum analyzer measurement. So the spectrum measurement was running, and then they pressed the frequency distance button, and it brings up the frequency display to where they can go ahead and enter in the correct frequency span, you know, if they're going to do start or stop, those kind of things, if they want to put a frequency offset in or if they want to use the channel number. So that is the front panel navigation on the test set, and so now we'll take you through a little demo here. So I'm going to go ahead and press the bottom left mode key, and it's going to go ahead and bring up the spectrum analyzer. I'm going to go ahead and enter in a channel number here. So I'm going to select my center frequency, and I know I've got a signal here at 780. Yeah, let's do 751. That's a downlink signal. And again, it does show up here with the little box. So once I press the frequency button here, it brings up the entry box, and so then the numeric keypad takes over the hotkeys. So once I enter that in, I can select my unit. The entry box goes away, and now the hotkeys themselves are operational, both the measure setup, the save load, those types of keys. Again, I can go into my frequency button here, and I can see my signal down here at the bottom, see my span. Again, I can change my channel number, go ahead and change my channel standard, all the standard things that you want to use going from channel to frequency. Again, if I wanted to throw a limit line on this, I can go over to my plus minus key here, select my limit. Back out of the entry mode here, so we'll go into the limit button. Okay. I'm in the wrong spectrum analyzer. I was in LTE FDD, so I'm going to go to my spectrum analyzer now. My spectrum measurement, I do have my center frequency and my span. Now I can go to my limit line. It brings up my limit line interface. I'm going to go ahead and turn my limit line on, and then I'm going to set the reference level, and I want to make it about -85 here. So my display line, I'm going to go ahead and select that. My entry box comes up, and I'm going to go ahead and enter in -85 dBm. And so now I've got a limit line here. And again, I can, through my save load here, I can go ahead and have it log data over this limit line. I can also turn on a multi-segment, and so I can build any waveform shape here I want on the screen. For amplitude and scale again, I can go and change my reference level, move it up or down. I can turn on my preamp. When I do that, I'm going to see my noise floor drop here, and this signal's going to go off the screen because I'm increasing the signal to noise ratio about 10 dB. So I'm going to go ahead and hit my reference level here and move the signal up just a little bit. My limit line moves along with it. So now I can see a little better representation of this 10 meg wide LTE carrier here. Again, I do have a trigger button. Let me go ahead and set my signal level here. There we go, trigger button. And then we have our measurement setup here, number 4. So again, under measurement setup, you will find an RF source under the spectrum analyzer. So you can turn on an RF source to output a signal that you'll be able to see on your spectrum analyzer. Again, if you need to use a CW source, that type of thing. So that's the basic front panel operation of the test set itself. Well, let's go in and look at the trace display. So again, you see here in the bottom left corner, you see a legend here. So the current live running trace is the yellow here, trace 1. So I'm going to go ahead and turn on, I have trouble seeing the dark purple here, so I'm going to go ahead and turn on trace 2. So I'm going to select trace 2. I'm going to go ahead and turn it on, and I'm going to set it as a min hold. And we should see these two separate. The minimum should drive further down. I'm going to go ahead and turn on trace 4. And set that to max hold. And again, now we've got a min and max. And so you can see the variance of power across here. So at times we're seeing power levels that jump up to about neg 90. At other times we're down around neg 120. And so there's about a 30 dB delta between the noise floor here on the downlink and the max power that's been seen at any one point of time. So as we move through frequency versus time versus power, you can see the variance here of those two signals. And again, if I select a specific button, right now it's set at unlimited for max hold, but again, I can set that for 5 seconds here, and we'll see the max hold disappear every 5 seconds and then come back. There we go. And then you'll see it build back up again. So again, this is fairly handy if you're using this test set to drive a specific route and look for interference. You want to see if there's a spur or something that comes up into the screen. You can set the max hold for, say, every 30 seconds, and you don't have to continually watch your test set as you're moving through the network. You can glance over once every 30 seconds or at, say, every stop sign or every stop light and look to see if there's a spur in this max hold here that comes up. And then you know, okay, I can either go back to the 2 blocks I just drove through, or I can go ahead and let it clear off, and I can move through the next 2 blocks to reevaluate. So again, a lot of useful features for interference and noise hunting on the trace display. Same with the markers. The marker display is here in the bottom. So again, once I select marker, it's automatically going to turn on marker 1 that we can see on the screen here. It's at the center frequency of 751 megahertz, and it gives us a power level here in dBm. Again, I can use the rotary knob here to move the marker around on the screen, or I can use the arrow keys to move the marker left or right. I can also use my peak search here to do the min search, peak search, next peak right, next peak left, so you can jump these around on the screen. So again, a lot of useful features on the test set hard keys here and on your hotkeys. So let's go ahead and move into understanding and performing power measurements. And so this is probably something that people haven't done in probably several years. I can remember back in the early 2000s on Sprint's CDMA network having to set power on lucent mini cells. You know, we don't even call it lucent anymore. It's ALU now, or alcatel-lucent. And one of the things we found back in early CDMA days is that power is very important for CDMA signals because CDMA is an interference-limited system. We went from GSM that had a fixed network capacity or amps that had a fixed network capacity to CDMA, which had a variable capacity based on the amount of power going to each user. There was a fixed amount of power you could output from an eNode B, and that power was designed to cover a specific area. And one of the things we found out is if you can reduce the power level to the minimum, you can actually get more users on the same span at the same time. And so one of the things we found back then is just a 1 dB delta, plus or minus 1 dB, can equate to about a 25% reduction in capacity or network coverage. So if you have a coverage hole, it's possible your power is only off by plus or minus 1 dB. And again, this little small center red circle here is a minus 1 dB coverage. So if you have a cell planning that's designed to have power, say, at 40 watts, or 40 dBm, I should say, and it's running 1 watt or 1 dB below that value at neg 39, you can actually have coverage holes that show up between the three different sectors that are supposed to provide coverage for that area. So you end up with a dead area or a place where you have calls drop. And I've seen this in places in California and Washington, various other markets that I've been through over the years. The same goes for if you have power that's set 1 dB too high, basically you get too much signal into a specific area. And with LTE, having too much signal out at the boundary areas can lead to, again, reduced capacity because the schedulers are looking to see what sectors close by are using resource blocks at that particular location. And so these things coordinate over the X2 link and will not assign resource blocks to a user in one area if it's being used by a user on the boundary from another area. And so having accurate power control is really pretty important. And so again, if you have too low a power, you're going to have low signal. It, may even be buried in the noise. And if you crank this thing up too high, here we've got an example of plus or minus 1 dB. But if you really crank the power up, and I've seen this in areas where people used to just go change out radios. They'd just pull out one and plug another one in, and they wouldn't bother to set the power. And maybe the radio was already programmed to output power at, say, 50 dBm, so it was way over driving the amplifiers. And what you can get there is you can get a lot of distortion that pops up. You'll see these spurs that'll pop up in the network causing interference issues. You can also damage your amplifiers by having too much input power into them. You get things such as clipping. It drives it past the saturation point. You get distortion in the digital signal. Your frame error rate rises. All those types of issues from that. So as far as power setting goes, there's probably only a couple places today you're going to directly measure power. Today with remote radio heads out at cell sites, the radios are up on top of the tower. And unless you have a tower crew, it's going to be very difficult to really get somebody in to, climb the tower, take the test set to the top. Again, you can run the test set remotely, so you can stay at the bottom and a tower technician or a tower climber can take it up on top and connect it in for you, so you can make these types of measurements. But it's a very expensive proposition. So the primary place you're probably going to use a directional power meter today is going to be in a distributed antenna system, say in a stadium or an arena, a place where you can get to the radio room itself and connect on directly to the output of the remote radios. And you can actually measure inline power through each of these links, both with this particular test set, both RF power, and it does come with an optical power meter. So you can measure both the optical light coming through if you have CPRI going from the BBU up to the DAS head end or distribution points, or if you have RF cables, you can put your inline power meter there and measure that directly. And again, a plus or minus 1 dB can really affect coverage and interference and capacity in an area like an arena, public center, those types of things. So you get a lot more capacity, a lot better performance by having accurate power measurements. And a lot of the DAS systems themselves, just because you type in 30 dBm doesn't mean you're going to get a 1 watt output. It can definitely be off a little bit based on the type of unit or the calibration of that particular unit. So we've seen that in a lot of instances. So what are we talking about when we're talking about measuring power? So if you think about just a light bulb, which is a load here, in your house, basically, if you have a power switch here, you turn on your power switch, and if it's just something like a flashlight, you know, you put 4 volts into a 4-volt light bulb, and you're going to get a certain amount of light out of the light bulb. If you put a 6-volt battery on it and increase the voltage, you're going to get a brighter light, more power. Your current is going to increase. The same can be said of an RF system. The problem becomes once you get high enough in frequency, then you start getting standing waves that are built on the mixing of the various frequencies that are all placed together on the RF cable on the transmission feed line. So with a standard light bulb, you basically have one set of power. It's a 60 cycle signal that's going through at a certain amplitude, and it's going to give you a certain amount of power. But with RF, you have a lot of different frequencies over, say, a 10 or a 20 meg span. And when you start getting those frequencies that mix and sum, now all of a sudden it's a lot more difficult to measure power with just varying voltage. So with those types of systems over 1 gigahertz in frequency, you really have to have an average power meter versus trying to use something like just a voltage setting where you crank up the voltage a little bit. And so that's really the delta between, a standard DC or low frequency system being able to set power where you can just use voltage versus a high frequency system where you really need to use a good average power or peak power measurement. And again, once you get up high enough in frequency, what you're going to see is incident waves going up the transmission feed line at various frequencies. You're going to get some reflection coming back based on the various frequencies along that line. And so the impedance that you're seeing at your power source is going to see some of that signal come back as a reflection. So what are we really talking about when we're talking about power? Power is just work done or energy transferred per unit of time. So you're wanting to take some energy and transmit it out your antenna, and that energy needs to be able to transit through the free air to the antenna on your user and be able to be read as a valuable signal at that particular point. The basic unit of power is the watt, which is basically 1 amp times 1 volt. But hardly anybody talks in watts these days. Most power is described as a decibel or a dB. And so if you're just using a standard dB type of terminology, that's a ratio of one signal versus another signal. If you want to measure absolute power, that is in dBm, which is power in reference to a 1 milliwatt signal. So again, there's a couple different values here. One is a ratio. The other is an absolute power in reference to a 1 milliwatt signal. And so here's a little bit of a chart that shows us the differences between power levels. So again, 0 dBm is 1 milliwatts. And if you look down here at the bottom chart here, so a change in dBm by plus 10 dBm, it's going to change your watts by 10. So if I have a 30 dBm signal, that's equal to 1 watt. If I bump it up by 10 dBm, it's going to go up to 10 watts. Again, if I go up another 10 dBm, it's going to go up to 100 watts. So you can see a 30 dB signal, if you have a 30 dB range on that, it can go all the way up to 1 kilowatt temporarily or momentarily. Same if you reduce the signal by 10 dB, it's going to divide by 10. So I think most people look at the 3 dB rate where the signal either doubles or halves. And again, just a change of plus or minus 1 dB equates to about a 25% change in power related to the watts. So again, this is a pretty good chart to be able to convert from watts to dB. And here's dB watts. So this is where it's in reference to a 1 watt, where dB watts is equal to 0. Again, that's at a 30 dB fixed point. So a couple different ways of looking at power. So what are we really talking about when we're talking about power? So we're talking about various frequencies that are summed up and the amplitude of those frequencies across a specific span. And what we're looking at is to see what power is encapsulated in that signal at any particular instance. And so you can see over time that particular power in a specific frequency is going to change. So here we've got a lower frequency, here we've got a frequency that looks like it's about twice as high. And again, these are both going to sum together through the first part of the cycle, but at some point, one signal is going to start decreasing in power, and the other signal is going to continue to go up. And so here, again, is looking at what you would see on a spectrum analyzer display with amplitude and frequency. Say you have two CW signals that you're looking at. If we look at those in a time domain, say with an oscilloscope, instead of seeing two discrete frequencies, you're going to see one sum of both of those frequencies. And so as those signals add up over time, you're going to see the power vary based on the way the frequencies interact. So again, as they both go up, the signal is going to continue to go up. But once one frequency starts to reduce back down in power, your amplitude here for the time varied signal, the compilation of all those frequencies is going to start to decrease. And you can see it here is basically the change in power over time when you sum two different frequencies together. So here we have just these two CW signals, and this is the power over time. So if you were to look at these in a spectrogram and see the power marching up in the screen over time by mixing these two frequencies, you would see the power get hotter, or the value of the power would get higher. It would drop off, get higher, drop off. So you'd see that change over time. And again, it's power transferred over a specific period of time. So why do we measure average power? Again, with some signals, you want to look at peak power or pulse power. And that would be like GSM is the only modulation format that I know that you really measure a peak power when setting power, because it is a time slot based. It's not continuously being transmitted. It's, one user gets, say, time slot 1 and time slot 4. And so the signal is off the other periods of time. So you're basically looking at just a peak power for that particular measurement. But for CDMA, UMTS, and LTE, which is sort of a pulse power, you're really wanting to measure an average power because it varies so much over time. And so they take the power, they measure multiple averages or multiple repetitions of the modulation cycle, and then they give you an average power reading for that particular signal. So again, here you can see how the power changes over time on the spectrograph for this particular 10 meg carrier here. Well, I guess this is a 5 meg carrier here. And so if you were just to measure the instantaneous power here, the peak would be the highest point you see at any particular instance, and average would be a line you would draw through this. But again, it changes at such a rapid rate here that you have to measure average power over several particular time slots for LTE. So again, you can see here at 5 dB per division, you can see there's 3, 4, 5, 6, 7, 8 different time slots here. So that's about a 35 to 40 dB delta between the peak and the min over this particular range here. And if you take the average power here, the peak to average ratio can be anywhere from 12 to 15 dB. So again, if you look at the amount of power that's being transmitted, if your average power is set to 30 dBm and you have this sort of crest factor, which is the difference between average power and peak power, if you go up 15 dB or 12 dB on this, that can be up to 100 watts difference between peak to average. So it's a varying time rate of power. So again, average power is really the way to make these measurements. So again, this slide here basically just talks about peak power measurements. Again, this is a GSM pulse. So again, it's measured at the top of the pulse here. You also have a pulse amplitude. Average power would be the power measured over multiple of these particular cycles here. So again, understanding which type of power you want to measure is critical for the type of system you're working on. So how do we actually use the power meters? So there's a couple different types here. So we have an external RF power sensor that basically plugs in either to the USB port of your test set, or we also provided software where you can run that particular power sensor off your laptop. It has a slightly different user interface. Today I'm going to focus on the test set interface. And the power meter that came, or the power sensor that came with your kit, is a directional in-service measurement. You can also purchase separately terminated out-of-service measurements. So we also have the capability to use an internal RF power measurement, and this just uses the spectrum analyzer measurement. And again, it's based on resolution bandwidth and does some signal analysis in there on the specific type of signal. We also have the capability, and I think with each one of the kits, you also have an optical power meter that allows you to measure optical power on a particular system. And again, you can use both an optical power meter on the DAS system to look at optical power between each one of the individual elements, or you can use the RF power meter to measure RF power between each one of the individual elements to make sure that at one point or another across the span, you're not seeing the power in a range that's unsuitable or can cause distortion or is too low to where you're going to have capacity and coverage issues. So here is the directional through-line power sensor. Again, it does have an input and output port on it, and I'll show you a little bit more about that here in just a second. It does have a USB client port on the bottom. There is a serial port too, but I don't know of anybody's laptop today that has serial ports on it. We also have the USB-based optical power sensor. So again, this directional power sensor can measure both average power in the forward direction, and it can measure average power in the reverse direction. And if you use these two power measurements, we can actually get a voltage standing wave ratio. So again, you can pick up incontinuities in the antenna feed lines while the system is under load. And so this is another indicator that would point you to having a mismatch or problems in your antenna feed lines, similar to PIM, using this VSWR measurement. So this particular power meter can also measure both peak and pulsed power. So here are the power detectors that are built into the directional power meter. So in the forward direction, we have a power sensor, basically coupled to the antenna feed line here, that can measure both average power or can detect peak power. In the reverse direction, we have a similar type of detector, but you only measure average power in the reverse direction. You never have to measure peak reflected power because it doesn't really count in the reverse direction. So again, this power sensor can measure both forward average power, reverse average power, and peak power. And again, you can connect it up either to your laptop or to the test set. It is possible also to purchase a terminating power sensor. So this just goes directly on the end of the cable, and it absorbs all the power output by the eNode B. For this particular type of sensor to work, you do have to have the right frequency range and the right sensor type. So these are specific for average power or peak power. You also need to use the attenuator that's included in your kit and take that into account for the signal drop. So I think these are a 40 watt or a 40 dB 50 watt attenuator. So it reduces the signal power down to a level to where your test set can read it directly. You can also use this attenuator with the spectrum analyzer type of power measurement directly on the test set itself. But again, you need to drop the power down to where it's in a range that your test set can handle. The max power for the test set is plus 25 dBm, so a little less than 1 watt. So if you're putting out a 30 dB signal, it is just slightly over what the test set can rate. And there you're running right at the max limit. And so you want to drop this down probably to minus 10 dBm range to get accurate power measurements to account for any headroom or crest factor that's coming through the cable, so change over time. So these are the power measurements when you go into the power measurement screen, so I'm going to jump back to my test set interface here. I'm going to go ahead and go to my mode button. I'm going to hit my more screen here because my power meter is on the second set of measurements. And when I go into the power meter, there's three types. There's my internal power meter, which uses a spectrum analyzer, channel power type of measurements. Here's my external RF power meter. It'll go ahead and load up. I do have my power sensor. Oh, I do not have my power sensor plugged in, so let me go ahead and plug it in. And it'll power up. And we'll go ahead and select it again here. There we go. And as you can see, we have 4 different types of power measurements. We have forward average power, reverse average power, forward peak power, and pulse power. And again, we do have a voltage standing wave ratio measurement based on both forward and reverse average power. So the setup on these are all the same. So once you select the specific type of measurement you want, then you're going to go ahead and hit the measurement setup key. So you can see we're in the mode for power meter. We're in the external RF forward average power meter measurement. And once I select measurement setup, then I can go in and change this resolution. And so right now it's set to 1 decimal point. So again, I can select 2 decimal points here if I want to of resolution with the power meter. It's capable of making measurements in that measurement range. Again, this particular power meter runs in a range of plus 21 dBm up to 150 dBm. So it's a very broad-ranged directional power meter. It also operates anywhere from 300 megahertz up to 3.8 gigahertz. So you can measure power on signals in any of those ranges. For average power meter, you also need to go in and select the technology type. So under technology type, you can select LTE, WCDMA, CDMA, EVDO, WiMAX. The TDS is a pulsed TDD type of LTE signal, or you can also measure TD SCDMA that's used in China. So the TDS type of signal is a time division synchronous. So it's using a single carrier for both uplink and downlink versus using a duplex signal that operates at a separate band for uplink and downlink. So again, you go and select your technology type. Then you need to set the frequency that you're going to measure. So if you're down at cell band, you're going to want to put in the frequency of the channel you're measuring. If you're up at 2100 or 1900 or down to 700 megahertz range, you're going to enter in the frequency of interest. And again, you'll see it update on the display. You'll see the type of power meter you have. And you can also set the amplitude of the screen. So again, if you need to measure power up to, say, 30 dBm, you'd want to change the amplitude scale from anywhere from 20 to 40. So you'd be able to zero in the power into the correct range on the screen. Again, if you're using an attenuator on the system, say a directional, or I should say a terminating power sensor, then you would use the 40 dB attenuator, enter that value in here so you'd still get correct readings on the screen here, even though your signal was attenuated down. You can also set limits. So if you go to your limit button on the hotkeys, you can put in a high and a low limit, so you have a range that you can enter in. Once you see the indicator arrow or needle move into the correct green range, you know you've got it set for your limits. So again, forward peak power sets up the same. Your SWR measurement gives you a range of reflection here of both forward to reverse power. And so again, you can measure a SWR measurement here, your voltage standing wave ratio. We also have pulsed power. And again, this does give you a signal here down in the line chart at the bottom where you'll actually see the cycle that it's measuring the power over, both the ramp up, for the pulse, the drop down, the next peak. So you will see your repetitive signal moving along the bottom of the screen here as you're measuring your external pulse power. So you should see the waveform here in the bottom screen. For the optical power sensor, same basic setup. You plug in your USB-based optical power sensor. You can set it either for automatic or manual wavelength measurements. And you, under manual, can go down and actually select the wavelength of interest. So whether it's multi-mode, single mode, whatever you want. If you have specific optical network that's using a different wavelength, you can edit a file and store that particular wavelength and pick it out of a stored list you have. So again, it's going to give you the power level. Right now, I don't have a way to generate a signal, either RF or optical here in my home office. So you can see it just says low. But you can measure optical power at each stage across your DAS system, or RF power using your average power meter across your DAS system. So one of the other areas you're probably going to see power measurements come back into fashion is going to be once we start looking at 5G, where they're going to be putting small cells, say, every 50 meters. Power control then is going to be very critical on a network. And so you're probably going to see the need to measure small cell output power for these particular small cell networks. So as you cover a shopping center, it's very similar to a DAS system, where you want to make sure you have good capacity, not too much overlap, not too much self-interference from other sectors covering the same location. So a small variance in output power from a small cell or from a DAS can significantly reduce throughput based on self-interference in a very close, tight RF environment. So this is your power meter. It does operate over a very wide range. This is a view of the laptop software. Again, it just plugs into your laptop. You do have to install the software first and then go in and run an executable for the driver for the laptop to detect the unit. Again, it does measure average power, peak power, and it does have a voltage standing wave measurement. Again, it is a 300 megahertz to 3.8 gigahertz unit. Again, plus 21 dBm up to 51 dBm. I guess it's 0.15 watts up to 150 watts. It does have a broad temperature range support. So this unit does operate anywhere from 0 to 50 degrees C. There is no calibration needed whenever you plug this unit into your laptop. It does have all its cal factors loaded into the power meter, but it does have an annual cal cycle. So if you are using this unit on a regular basis, I would recommend getting it caled once a year to maintain the accuracy. Again, you can store this down anywhere from neg 20C to 70C, so a very broad temperature range. So whether you're in Phoenix or Minneapolis, you should be able to leave this in your vehicle in your kit and not have to worry about it damaging the components inside. Thank you, and I appreciate your time.